Alright, so let's continue this time with our solving our log equations. Alright, and here we have to check for extraneous solutions. Sometimes we get those and we can't take the log of 0 and we can't take the log of a negative number, so we must keep that in mind. The left hand side we have 2 logarithms is equal to just a value. Now this is not, when we have a log equal to a log, then if they're the same base, if these numbers are the same, because these logarithms are one-to-one functions, the arguments must be the same. A would have to be the same number as C. We don't have that here. We have the subtraction, these 2 logarithms equals single value. We do have properties of logarithms that allow us on the left hand side to write this as a single logarithm. We have the quotient rule. Now remember that when you first learned these, we were taking the log of some value, like say 24, where we rewrote 24 as 48 divided by 2, and the log of 24 is equal to the log of 48 minus the log of 2. Well, if we had the log of 48 minus the log of 2, we can express that as the log of 12, 48 divided by 2. So sometimes you have to, you'll look at this equation and you're thinking in terms of left to right, or other times you're looking at this equation and saying I have 2 logarithms and I can condense it to a single logarithm, and that's what we're doing here. Alright, where'd we go? So let's take this guy, move it over here, and that's the first thing that we're going to do is these 2 logarithms that have the same base, they have a base of 6. We're going to express it as a single logarithm because we know the log of the numerator minus the log of the denominator. My numerator is x minus 5, my denominator is x plus 5. And we cannot simplify, we cannot come in and cancel these common terms. If it had been 5x, 5 times x divided by 5 times x, then yes. Alright. So we refer to this equation as being in log form. When it comes to solving equations, we're more familiar with it in exponential form. We want to step by step get the variable by itself, and since this does not mean log times this expression, we don't have any way of manipulating or getting this expression to get x singled out. But we can write it in a different form. The base of this is 6, that small value. This 6 has some exponent associated with it. Well, a logarithm equals the exponent. So this 1 here is the exponent for this base of 6, and that's equal to our argument, which is this fraction. Now, oops. I'm going to come back and rewrite 6 as 6 over 1, and this equation is referred to as a proportion. We had log form and exponential form. That's how we rewrote it. The exponential form, you've got some base raised to an exponent, but this equation itself is referred to as a proportion, and one technique to solve proportions is to cross multiply. So if we multiply along this diagonal, we've got 6 times the quantity x plus 5, and if we multiply along this diagonal, we have 1 times the quantity x minus 5. Alright. Let's distribute the 6 through. And and put a 1 there to visually to help us. So we've seen these type of equations before. You have variables on both sides of the equation, constants on both sides. You want to get the variables on one side and the constants on the other. I'm going to collect all of my variables and write them on the left-hand side of the equation, and all my constants, the values that do not have variables, the terms that don't have variables, collect them on the right-hand side. So if I subtract 1x from each side, then I've accomplished part of that. I've got 6x's, take away an x, it leaves me with 5x's. 1 minus x, take away 1x is just 0. 0 minus 5 is negative 5. Alright, so now let's add 30 to each side. And finally, let's divide by 5. So my possible solution to this is 5. So let's come in and check to see if that's extraneous or not. Let's plug in 5 into our, on the left-hand side, we have log base 6 of 5 minus 5 minus log base 6 of 5 plus 5. And the question is that subtraction, does that simplify to 1? Well, right away we've got a problem. We have 5 minus 5. We're taking the log of 0, and that's undefined. So there's no way that we can perform this subtraction, because you subtract numbers, and this first value is not a number. Log base 6 of 0 is undefined. There's no real number that satisfies that, so we say no solution. This is extraneous. It was our only candidate for a possible solution. With it being gone, we have no solution. Alright, let's take a look at number 10. So we see a similar problem. We started out, oh, excuse me. Like I say, it's very early in the morning here, and I don't think I've fully woken up. We have the difference of two logs. Difference is just another way to say subtraction, is equal to a value. So by my properties of logarithms, we're going to use the quotient rule and express this subtraction as a single logarithm. Log base 5 of x plus 3 is my numerator. X minus 5 is my denominator. This equation is referred to as a log form. And we can rewrite this as an exponential form. We have a base of 5. This base of 5 has some exponent associated with it, either this guy or the 1. Well, since a logarithm equals an exponent, it's 5 to the first power is equal to this fraction. I'm going to write 5 to the first power is 5 over 1, and this exponential form, the equation itself is referred to as a proportion, and one technique to solve proportions is to cross multiply. So I'll multiply along this gray diagonal, I'll multiply along this yellow diagonal, and let's see what we get. Multiplying along the yellow diagonal, 1 times x plus 3, we just get back x plus 3. Multiplying along the gray, we've got 5 times the quantity x minus 5. We need parentheses there. Make sure that you do that. Distribute the 5 through. Multiplication distributes over addition or subtraction. So both these binomials, both terms here, get multiplied by the number 5. So let's get the x is on one side and the constant's on the other. If I subtract 5x from each side, don't forget that negative sign that's in front of the 20. I subtracted 5x. I suppose I could have subtracted 1x from both sides to avoid that negative value, but that shouldn't bother anybody. Let's subtract 3 from both sides. Three minus 3 just gives me 0, and when you add 0, you get the identical thing back. Negative 25 minus the 3 is negative 28. The inverse of multiplication is division. We'll divide both sides of the equation by the coefficient, divide both sides by negative 4. We have a possible solution of 7. Because negative 28 divided by negative 4 is positive 7, let's plug it in. Let's look and see if it checks. On the left-hand side of my equation up here, if I plug in 7, I have log base 5 of 7 plus 3 minus log base 5 of 7 minus 5. So 7 plus 3 is 10. Seven minus 5 is 2. When you have the difference of two logs, you can write it as log of the numerator minus that log of the denominator. And 10 divided by 2 is 5. And it's true that 5 to the first power is equal to 5. So this does check. You take your answer and plug it in. On the left hand side does equal the right hand side. So I am getting an answer of D. Let's continue with number 11. Again, I have subtraction, so and it equals a value, not a logarithm. We've got the log of the numerator minus the log of the denominator. We can change this to exponential form. This base of 4 raised to the first power is equal to, don't know why I made that so big. Alright, so let's rewrite 4 as 4 over 1. This is this exponential form. This is a proportion, and one technique to solve proportions is to cross multiply. Alright, so we've got 4 times the quantity 1 minus 4x is equal to, well, 1 times 3 is 3. Let's divide both sides by 4. Let's subtract 1 from both sides. You can let the calculator do the work here. To subtract 1, well, I want to rewrite 1 as 4 divided by 4, so they have the same denominator. Oop, I lost my x. 3 minus 4 is a negative 1. Let's continue up here. Negative 1/4 divided by negative 4. We can rewrite division as multiplication times the reciprocal of negative 4. Negative 1/4. Negative 1/4 times the negative 1/4 is positive 1/16. Let's get a decimal number for that. And it's choice D here. 0.0625. Let's take a look at the next one. Alright, so this one we see is slightly different. We have natural logarithms instead of a common logarithm or log base some other value. Natural logarithms are just log base e. But on the right hand side, we also have a natural logarithm, and we didn't on the right hand side before. We had just values, just the number 1, the number 1 again. So this one's going to be slightly different. We start out in the same way. On the left hand side, we've got two logarithms. We want to use our product rule to write it as a single logarithm. We have the log, well, we actually have the natural log plus another natural log. We want to rewrite that as the natural log of the product a times b. Alright, so we can write this left hand side as a single logarithm if we take the product of these arguments, 4 times the quantity 9 minus x squared. Well, 4 times 9 is 36, and 4 times this x squared is just 4x squared. So remember that exponential functions and log functions are one-to-one. If these two numbers are the same and the bases are the same, these arguments have to be the same. So this 36 minus 4x squared is the same value as 35. Alright, so we want to get our variable by itself. Let's subtract 36 from both sides. Do not forget the negative sign that's in front of your term that has your variable. And let's divide both sides by negative 4. Negative 4 divided by negative 4 is just 1. If x squared is equal to 1/4, then taking the square root of both sides, we have to introduce a plus or minus. To take the square root of a fraction, you can take the square of the numerator divided by the square root of the denominator. Square root of 1 is just 1. Square root of 4 is 2. So we're having possible answers here of negative 1/2 or positive 1/2. So we have to check these to see if they both satisfy the original equation, make sure that one of them is not extraneous. So let's come over here and let's check. And we'll start out with negative 1/2. On the left hand side, we've got the natural log of 4 plus the natural log of 9 minus negative 1/2 squared. That equals the natural log of 4. Negative 1/2 squared. Negative 1/2 times negative 1/2 is a positive 1/4. Let's rewrite the number 9 with a denominator of 4. 36 divided by 4 is 9. Subtracting 1/4, we have 35 over 4. If you have two logarithms of the same base and you're adding them by the product rule, you can multiply the arguments together. So we've got 4, I'll write as 4 over 1 times this fraction 35 over 4. 4 divided by 4 cancels. We have the natural log of 35, which is what it stated. So we know that negative 1/2 is going to check, and it's easy to see that positive 1/2 will as well, because if we check this positive 1/2, when we squared the negative 1/2, we got 1/4. When we square positive 1/2, we get 1/4. From there, everything is the same, so this one checks as well. And 1/2 as a decimal is 0.5, so we see that we had plus or minus 1/2 is the same as writing plus or minus 0.5. And like I say, that's negative 0.5 or positive 0.5. And that's choice A. Alright. Let's take a look at number 13. Again, we see on the left-hand side, we see that this is a log equation. On the left-hand side, we can combine these two logarithms as a single logarithm by recognizing its log of the numerator minus log of the denominator. This equation is referred to as a log form, and now I suppose, no, I can't simplify. Let's change this to an exponential form. The base is 3. This 3 is going to have an exponent, and the logarithm equals the exponent. Alright, so this is exponential form, but the equation itself is referred to as a proportion. We can write 3 as 3 over 1. One technique to solve proportions is to cross multiply. Multiplying along this diagonal, and then set that equal to multiplying along that diagonal. If we multiply along the yellow diagonal, 1 times anything, you get that identical thing back. Along the gray diagonal, 3 times 6 is 18. Subtracting 9 from both sides of the equation, because we want to step by step get the variable by itself. Let's divide both sides by 4. 4 divided by 4 is 1. To get the x by itself, let's extract the square roots. In the process of taking the square root here, I have to introduce the plus or minus symbol, because this radical means the positive square root. And when you're taking the square root of a fraction, you can take the square root of the numerator and the denominator separately, and since those are both perfect squares, we get either negative 3/2 or positive 3/2. We need to check these answers. So if we're checking negative 3/2, what do we have? Well, on the left-hand side, we've got the log base 3 of this negative 3/2 is going to replace x and it's being squared, so the negative 3/2 is squared. And we want to see if this subtraction problem reduces down to 1. Alright. When we square this negative 3/2, we get a positive 9/4. The 4 can be written as 4 over 1, and you have times 9 over 4, and 4 divided by 4 is 1, and 9 divided by 1 is 9. Plus 9 plus 9 is 18. And 18 divided by 6, because we have the quotient rule that says if you have the log of a quotient, it equals to the difference of the logs, or we're looking at it in the other direction, saying if you have the difference of two logs, you can write it as a single logarithm. And 18 divided by 6 is 3, and log base 3 of 3, well, 3 to the first power is 3. Remember that logarithm equals an exponent, so hey, this does equal 1. So our positive and negative 3/2 did check, and on a 3/2, positive or negative 3/2 is equivalent to positive or negative 1.5. Just take 3 divided by 2, half of 3 is 1.5. So we get an answer of A. So I'm hoping this helps, that it is helping. Alright, we've got 14, 15, and 16 left to do. They are of the same technique. We have a log plus a log equals a number. We have a log minus a log equals a number. Log minus a log equals a number. So in each of these last three problems, we're on the left-hand side, we want to condense it and write it as a single logarithm. By the product rule, when you have addition, you multiply the two arguments together. So take 10 and distribute it through the 5x squared plus 3. And that is equal to the number 5. That's in log form, so let's rewrite it in exponential form. The base is 2. This 2 has some exponent associated with it. The two choices, 5x squared plus 30 or 5. Well, the pattern is that the logarithm equals the exponent. This is a quadratic equation. For quadratic equations, we want to get them in standard form. The standard form for a quadratic equation, yeah. Let's back up a second. We went from log form to exponential form, and this equation, in our previous examples, they were proportions. Well, this is a quadratic equation, so we want to get it in standard form. Ax squared plus bx plus c is equal to 0. Identify a, b, and c, and we can use the quadratic formula if it doesn't factor. If it factors, we'll use that because that's generally a quicker solution. So, returning back to our problem here, if we subtract 2 to the 5th power is 32. If we subtract 32 from each side, what do we get? Well, on the left-hand side, we have 0. On the right-hand side, 50x squared minus 2. So in standard form, we don't have a middle term, we don't have an x term, so that means we could still use the quadratic formula, but before I said, well, factoring, well, with this middle term, we don't have to factor it, we just have to get the x squared by itself. So actually, now that I have this in standard form, I'm going to turn around and add 2 to both sides. And I get that 2 is equal to 50x squared. Let's divide both sides by 50. Alright, so 2 divided by 50 reduces to 1 over 25. 50 divided by 50 is 1. So now if we take the square root of both sides, we get x is equal to, we have to introduce the plus or minus the square root of 1 over 25. When you have a fraction, you can take the square root of the numerator and denominator separately, and the square root of 1 is 1, and the square root of 25 is 5. So we're getting negative 1/5 and positive 1/5 as decimal numbers. That is negative 0.2 and positive 0.2. We see that as a choice, but we also see no solution. What happens if both of these didn't check? So let's come over here and check these to make sure. Oops, I thought I had. Alright. Negative 1/5 and positive 1/5. So when x is negative 1/5, let's plug it into the left hand side. Alright, so let's do this arithmetic. Negative 1/5 times negative 1/5 is 1 over 25. Because a negative 1 times a negative 1 is positive 1, and 5 times 5 is 25. And we see that 5 times 1 is 5, 1 times 25 is 25, 5 over 25 reduces to 1/5. We're going to rewrite this number 3 with a denominator of 5 so that we can add these. So I'm just going to multiply by 5 over 5. 3 times 5 is 15. So 1/5 plus 15 over 5 is 16 over 5. We have the product rule that we can take the sum of these two logarithms that have the same base and multiply their arguments together. And we can simplify that 5 goes into 5 one time and 5 goes into that twice. So we have that 16 times 2 is 32. Alright. Now the question is, is log base 2 of 32 equal to 5? Well, it is equal to 5 because 2 to the 5th power is 32. So the negative 1/5 checks. If we think about what positive 1/5 would be, would it check? And it turns out that it will. I think it can be easily seen. If we were plugging in 1/5 rather than negative 1/5, 1/5 times 1/5 is 1 over 25. So from here below, we get the exact same thing, the exact same steps that we did with positive 1/5 that we did with negative 1/5. So they both check, is my point. All right. Now, negative 1/5 and 1/5 as decimal numbers were negative 0.2 and positive 0.2, and that was option B. All right, so I hope this is helping. 2 more problems, and we're done. On the left-hand side, the difference of two logs can be written as a single log because it's the log of the numerator minus the log of the denominator. So that gives us an equation where we have a log on the left-hand side, but on the right-hand side we don't have a log. So we can't say that this ratio is equal to 2. We have to convert it to exponential form. The base is 6. This base of 6 has some exponent associated with it, and the logarithm equals the exponent, so it's 6 squared. If we make 6 squared into a fraction, we can solve this proportion. This exponential form, the equation itself is referred to as a proportion. And if we multiply along the yellow diagonal, multiply along the gray diagonal, set those equal to each other, and we have our equation to solve. Alright. So 1 times anything, I get the 4x squared minus 4 back. 6 squared is 36. 36 times 7 is 252. This is a quadratic equation. Now before, I just saw a quadratic equation and I immediately put it in standard form, but upon closer inspection I see there's no x term, so we can just solve this directly, getting x squared by itself. So let's add 4 to both sides. Let's divide by 4. And we have that x squared is equal to 64. And 64 is a perfect square, taking the square root of both sides. We get 8. But remember, we need to introduce the plus or minus 8 there. So that is a choice. There's not a choice of no solution. So on a test or quiz, if I was running out of time, I would just circle that and move on. But let's check and make sure that there's not a typo in the solution, that it is in fact choice C. So on the left hand side, let's check negative 8. Let's plug in, let x be negative 8 on the left hand side, do this subtraction, see if it in fact is equal to 2. So we've got log base 6, 4 times x is negative 8. So we have this log minus Alright, let's look at If I key this in a calculator, I get 252. The difference of two logs, I can write that as a single logarithm. The log of the numerator minus log of the denominator. And 252 divided by 7 is 36. And log base 6 of 36 is equal to 2 because 6 squared is 36. Remember that our logarithm equals the exponent, and 6 has to have an exponent of 2 to be 36. If we come in and check our positive 8, if this would have been positive 8, then that would be positive 8, and everything else is the same. So negative 8 and positive 8 checked. So our answer is, for number 15, is C like Charlie. All right, the last one. And we see it's similar to the previous ones that we've been doing. On the left-hand side, we have the difference of two logarithms. Log of the numerator minus log of the denominator. Alright. This is in log form. We want to rewrite it in exponential form. This 4 is the base. It has the logarithm equals the exponent, so this base of 4 has an exponent of 1, and that equals 4x squared minus 8 over 7. If we cross multiply, along the yellow diagonal, we have 4x squared minus 8. Along the gray diagonal, we have 28. Let's add 8 to both sides. And let's divide by 4. Taking the square root of both sides, we get positive or negative 3. So positive or negative 3 is a choice. I don't see a no solution, so most likely it's going to check. If I suppose it's possible we could have done a silly mistake and just by pure chance came up with one of the choices. But so let's check our answer just to be 100% sure. Negative 3. If we plug negative 3 into here, will the left-hand side equal the right-hand side? So the left-hand side of my original equation has log base 4. 4x squared is 4 times negative 3 squared minus 8 minus log base 4 of 7. Log base 4. Now, negative 3 squared is 9, and 4 times 9 is 36, and 36 minus 8 is 28. The difference of two logs can be combined and written as a single logarithm. This is log of the numerator minus log of the denominator. The numerator is 28. Denominator is 7. Hey, that's equal to 4. And 4 to what power is equal to 4? Well, 4 to the first power. So, hey, that equals 1. So that checks. Now, we were also wanting to know if this was true for a positive 3. And you can see that if we had squared positive 3. We had the same answer if we squared negative 3, so everything below there remains the same, and it does check. So both of those are a solution. So I hope this helps, and we'll talk to you later.